Uh, yes, I have started the recording, so you can
Okay.
start. We are at 11.
Yes. Hello, everybody. Good morning and good afternoon or good night if you're joining from other parts of the globe. Just a second. Folks, whoever is not presenting, please keep yourself on mute. So welcome to the talk by Dr. Nirupam. And this talk is being presented by the iMobile ACM chapter. This is the India chapter of ACM SIG Mobile. This chapter was started in March of last year, so March of 2019. The website information, everything is available. You can simply search for iMobile on Google and you will still reach this website. There are LinkedIn, Facebook groups and LinkedIn page as well. Emails are there in case you need to get in touch with us for anything. So the iMobile ACM chapter was formed in 2019 as an ACM community of researchers and practitioners in India with an aim to develop a greater passion for systems research in the country while adhering to the global charter of SIG Mobile. So traditionally we have seen that the presence of Indian researchers in conferences which are typical of SIG Mobile such as MobiCom, MobiHawk are much fewer than representation from some other countries. I don't specifically mean ethnically Indian because there are a lot of Indian researchers who publish from the US universities, but from Indian universities, the representation is relatively low. This chapter was opened in order to give this a push and see if we can get researchers from all over the world who work in relevant fields to talk about their work and help in disseminating information, what kind of environment is needed for this kind of research, what are interesting topics, what kind of papers get accepted, stuff like that, right? So in general, the scope of SIG Mobile is to perform research in the theory and practice of all areas related to mobility of systems, users, data, and computing, and expand the evolution of portable computers and wireless networks, improve access, service, management, and applications for mobile computing and communication. So I'm not going to go over everybody. We have an iMobile ACM chapter, and the team for this year consists of these fellows. I am Amit, I'm the vice chair. I'll soon hand it over to Sandeep, who is the treasurer. And there are a lot of other people who are involved kind of behind the stage, arranging the webinars, making everything is up and running, making sure everything is up and running, inviting speakers. And we also have some well-known mentors like Venkat, Suman, and Rajiv, who help us in guiding the charter of this chapter. Okay. So with that, I will now hand it over to Sandeep, who is going to introduce today's speaker, Dr. Nirupam. Sandeep, you can take over.
Yeah, sure. So thank you, Amit, for the introduction about iMobile chapter. So today we are delighted to have Dr. Nirupam Roy as a speaker for our webinar. So Nirupam is an assistant professor in computer science at the University of Maryland, College Park. He received his PhD from the University of Illinois, Urbana-Champaign in 2018. His research interests are in wireless networking, mobile computing, and embedded systems with applications to IoT, cyber physical security, very much aligned with the focus of iMobile as well as SIG Mobile. So his recent projects include low power sensing techniques to enable self-defense in robots and drones. His doctoral thesis was selected for the 2019 CAD Thesis Award at UIUC. Nirupam is also the recipient of the Valkenburg Graduate Research Award, the Lalit Pal Fellowship, and the Outstanding Thesis Awards for both his bachelor's and master's institutes. His research received the Mobisys Best Paper Award and was selected for the ACM SIG Mobile Research Highlights. Many of his research projects have been featured in news media, such as the MIT Technology Review, the Telegraph, and the Huffington Post. So today, Nirupam is going to talk about a very interesting research topic on Internet of Acoustic Things. So he has long exposure starting from his PhD on acoustic communication and applying acoustic in different aspects of mobile computing and IoT. So today's topic is broadly covered about how acoustic can be effectively used for developing application and services for IoT. So Nirupam, over to you. You can share your screen now and
Sure.
initiate the talk.
Sure.
So
Thank
I
you so
request
much.
all the participants to please keep their microphone muted. And as Nirupam suggested that he will be happy to take questions in between. So whenever you have a question, you can unmute yourself and follow up with Nirupam. So Nirupam, yeah, please go ahead.
Thank you so much. Thank you so much for all these kind words, Sandeep. I'm delighted to be here today and talk to you about my research, the Internet of Acoustic Things. These are the research topics that I have particularly explored during my PhD at UIUC, and now actually building on them for multiple different directions. So I will briefly touch upon them. I'll mainly focus on my research that I have done during my PhD thesis. The topic is the Internet of Acoustic Things, challenges, opportunities, and threats. So let's get started. So it is well past 12 midnight here. And by the time I'll be done, it will be almost 1:30 in the morning. So please keep asking questions and make sure that I do not fall asleep. And feel free to stop me in between if you have any questions. Feel free to ask it right away. All right. So let me start with by saying that voice assistants such as Amazon Echo, Google Home have already started percolating to our houses, right? 15 million have already been sold, and market projections are absolutely staggering. But you know, this is just the tip of the iceberg. If you look around, you find that lots of technologies are surfacing, all centered around sensing and computing and processing acoustic data, sound data. For instance, Qualcomm, Bose, Neura, this kind of, trying to develop new kind of sound delivery system, sound generation system, and that is not only generating the sound, they're also trying to understand the perception of the sound, how the user is listening to different frequencies. And in order to do so, they are sending some signal into the ear canal to profile the shape of the ear canal so that they can generate sound accordingly that can exactly fit the requirement of the user. On the other hand, companies like Google, Leapmotion, they're embarking on fine-grained gesture recognition. And in order to do so, they are sending some signal, some acoustic signal from the device. And if you are moving your fingers in front of that device, the reflected signal, they are analyzing the reflected signal to estimate some fine-grained features that will enable the next generations of human-machine interactions. And health-related technologies are also not behind. New wearable skin patches are listening to our human bodily sound and vibrations, and thereby coming up with new biomarkers that can continuously monitor our health. And that was not otherwise possible with any other kind of sensing modalities. And at last, let me talk a little bit about the uh, topic that is called holosonics. And this is a technique that I'm really interested in. And what they're basically doing, they're trying to beamform sound in a very narrow beam towards a particular direction. While that kind of directionality is hard to achieve, but they have shown that certain properties of the air can be leveraged to achieve this kind of a super fine pencil beam of sound. Now, all this technique around acoustic signals, and that is actually on the same board on a small computing device. So that is not particularly surprising, because it is the confluence of sensing, computing, and communications together that probably started with the smartphone and now happening at much finer granularities, and ultimately opening up a new opportunities, which is called the Internet of Acoustic Things. And my work, my PhD thesis work, was mainly centered around developing new primitives in acoustics and vibration that can enable new human-centric IoAT, Internet of Acoustic Things application. So in this talk, I will talk about I have actually picked 3 different topics from that thesis, and I'll talk about those 3 little disconnected, little different ideas, all that is actually in the umbrella of Internet of Acoustic Things. So let me give you a prelude or like trailer, like the movie. So I'll talk about the 3 different topics that I'm going to talk to you today. So the first one I call inaudible acoustics. So let me tell you what I mean by that. So if I play sound, normal sound, less than 24 kilohertz, then both human and microphones will be able to hear that sound, record that sound. On the other hand, ultrasound above 25 kilohertz, that is neither audible to human nor recordable by the microphone. But in this project, we are designing ultrasound such that it remains inaudible to human naturally, but becomes recordable by regular microphones. And if we can enable this inaudible acoustic, that is inaudible to human, recordable by the microphone, regular microphone, we can open up multiple applications, and at the same time, that can also open up, reveal some of the threats. For example, someone can use this inaudible acoustic to give inaudible voice commands to voice assistants, and the voice assistant will respond to those commands while human around that device will not be able to hear anything. So let me show you a video so that you can see this technique for yourself. Here in the setup, we have an Alexa, Amazon Echo device, and we have the human speakers and our inaudible acoustic system. So first the human speakers will give some command to Alexa, and then our inaudible speaker will repeat the same command, and you'll see that in both of the cases, Amazon Echo is responding in a similar way. So let me just play the video so that you can see it for yourself.
Alexa, what's the capital city of the United States? The United States capital city is Washington, D.C.
Now we are delivering the same command through this inaudible speaker system. We did not hear the sound, but Alexa is turned on.
The United States capital city is Washington, D.C.
So it responded just like it has heard a regular sound. So that is what I'll talk about in inaudible acoustic. And then I will talk about another project. It's communicating through physical vibration. Let me give you a little overview about this topic. We all know that smart devices have some tiny actuator, which is called vibration motor. That actuator is responsible for generating the vibration alert when our phone or smartwatch is in the silent mode. So we use that vibration motor as the transmitter. We designed ways to modulate the vibration so that the vibration can encode data bits and it can pass through human body. And if it does some motion sensor or some smart device that has this motion sensing devices, that sensor can decode this tiny vibration and recover the data. This particular technology, this communication through physical vibration, can enable touch-based communication, which is more secure than broadcasting the signal in NFC or Bluetooth. And if it is done well, then it can be used to transfer security codes to the smartphone, or you should be able to open your car door simply touching the door without requiring the key. Many other applications are possible. I'll talk about this topic in detail. And then, if time permits, I'll talk about a third topic, which is acoustic side channels. Here, we are specifically asking the question, can human voice be recorded without using a microphone? And we have shown that the motion sensors or other kinds of sensors inside the smartphone, they can also respond to this vibration that is being produced while someone is speaking, this air vibration that can also perturb those motion sensors inside the smartphone. And with the processing, with human voice recovery, we should be able to decode those human speech, and we should be able to record that human voice without using the microphone. Now, what are the applications? Well, we can use this vibrations as a secondary channel along with the primary airborne sound to remove an ambient noise, to have better sound recovery or speech recovery when you are trying to speak to your phone in a heavy noise. At the same time, this technique can reveal some of the attacks where some of the applications like the step detector application that should not have access to the microphone now can record, now can spy on your voice command or any voice that is you are trying to talk, or any voice that is going on in the environment. It can spy on that conversation and record it without having permission to record or access microphone to record anything. That can uncover this kind of threat. So I will quickly touch upon this topic as well. So before I go to this individual topic, let me generalize my research, and let me give you an overview how my research is actually developed. So I started from the very physical layer, sensors, actuators, and radios. And on the top of that, I've developed multiple building blocks, multiple primitives of technique, like inaudible acoustics, vibratory modem, acoustic side channels, that will ultimately lead to applications with voice interfaces, wearables, security, and also wireless and localization. While working on this space, I mostly draw from the techniques in networking, embedded systems, and also I actually borrowed techniques from signal processing, build on ideas of communications and learning. So next, I will go to the individual topic, starting with the inaudible acoustics, but please let me know if you have any questions at any moment as we start on this. Right? So let's start with the inaudible acoustic. Like I already mentioned, that if I play a sound less than 20 kilohertz, audible sound, it will be audible to human and recordable by the microphone. And in this project, we are developing sound that is much higher than that audible range, more than 40 kilohertz actually. And we are trying to keep it inaudible to human naturally, the way it should be. But we are trying to make it recordable by any microphone that we see around us. Now, when I say this to people, they often think that we are using the opportunity, the gap in the recording range of the human ears, operating range of the human ears and the microphone. It has a tiny gap in between. We know that most of the microphone, if they're running at 48 kilohertz of sampling rate, it can record signal up to 24 kilohertz, while most of the adult human hearing range is little above 18 kilohertz. So this gap is called near ultrasound. If something is being played in that frequency range, in near ultrasound frequency range, that will be inaudible to human, but recordable by the microphone. This is a small, tiny band that actually has been exploited and explored a lot by many interesting ideas in our field. But our idea, our inaudible acoustic, has nothing to do with this near ultrasound. Rather, we are generating very high frequency sound, more than 40 kilohertz. And we are designing the sound in a way that when you will pass through the hardware of this microphone, it will get transformed to the low frequency range, or it will get shifted toward the low frequency range inside the hardware. And when it will be recorded by the microphone, that shifted sound, it will appear like any natural sound to the microphone, but being high frequency sound originally, it will be completely transparent to human ear. So that is the key idea. Now, let's ask the question, what can we do with this? If we have that capability, what kind of applications we can enable with that? So I have a question. I have a question from Sushant Karmakar, who said that, do we know if any living being generate sound in this narrow band? Actually, there are some kind of animals, or at least some kind of insect like cicada, they can produce some signal between this 18 to 24 kilohertz that is inaudible to human, but can be recorded by the microphone. But that is off topic to us. We are mainly focusing on how we can generate very high frequency sound and wide band of sound, not only a narrow band, but design that in a way that it will be recorded by the microphone. Now the question is how we can use it.
So Nirupam,
Yes.
I have one quick question. Like, as we know that acoustic signals are very much prone to environmental noise. So for this range of inaudible acoustic signal, what is the impact of noise on it? Say, for example, if you want to, so within a gallery, well, still the noise is less. But if you want to use within a shopping mall, the noise would be pretty high, right? So
that's a very nice question and very valid practical question actually. So interestingly, if you plot the spectrum of all the sound that we see around us, we'll find that most of the energy is concentrated within 0 to 2 kilohertz. All the sound and noise and all the thirds, everything is very low frequency sound. Human voice can range reasonably up to 8 kilohertz. There may be some sound that can go beyond that, maybe 18, maybe the jingle of the keys of some metallic sound. Some music actually uses very high frequency sound to create different effects, also some low frequency sound. But interestingly, the higher frequency sound, more than 40 kilohertz, where we are planning to operate on, those sounds are much quieter. But so we have some advantage of having less noise at the frequency that we are generating. But at the same time, as I will go into the technique, when I explain the technique, it will be much clearer that this high frequency is getting shifted to the lower frequency range. So it will get affected by the ambient noise and all. But in our technique, while we are trying to communicate with high frequency signal or in this acoustic communication, we mainly try to use little higher frequency band, more than 8 kilohertz and within 24 kilohertz. So that range is much quieter and it has less ambient noise. So the communication can run at that space. I have another question, Mukulika Maithi. The range of acoustic communication is very small. Can we give an estimate of the distance of the high frequency acoustic communication? So of course, yes, the range is small, but the application that I'm going to talk right now, that will be very fitting to a low range communications. For example, if we are looking for a location-based information sharing, imagine that you are in a museum in front of a painting and you want to download some information about that painting. In this case, you inherently need some localization of the communication. Or you are in a shopping mall, you are next to a particular shopping rack. You need some localized information exchange for that. So in this case, the lower short range communications will be more appropriate, that is inherently localized. But in our experiment, we have tested with ranges from 3 meters to up to 6 meters to be able to communicate at various data rates. So these are the a few applications which are possible with this inaudible acoustics. Interestingly, let me introduce another kind of application. Imagine an important meeting is going on and someone is trying to sneakily record that conversation with microphone. As of today, we do not have any effective way to prevent this kind of acoustic eavesdropping, right? Because if you want to jam those microphones by generating some sound, loud sound, you will end up jamming the conversation in the first place, right? But with this inaudible acoustic, which is inaudible to human, but appears like regular sound to microphone, we should be able to build a jammer that can block all the microphone in that room without interfering with the conversation that is going on. We should be able to create an inaudible jammer with that. Another question, have high frequencies and harmonic been used to cure disease and living? So I am not going to that topic. Maybe towards the end, we can take that question. So while multiple applications are possible with this inaudible acoustic, there are multiple threats that can be possible with this inaudible signal. Imagine that the robbers are jamming all the 911 call or dial 100 calls before launching the bank robbery. Or like I mentioned, that inaudible voice command. There are multiple applications threat which are possible. But before talking about the applications in detail, let's try to understand how this magic of inaudible sound is possible, what is the technique behind this inaudible sound. So let me start with the absolute basic, right? How does this microphone work? It is nothing but a sensor that is converting air vibration to digital samples so that further computation can run on that digital samples. If you break open a microphone, you'll find essentially 4 different components. The first component is the diaphragm that responding to the air vibration and converting that air vibration to some voltage, some electrical signals. Those electrical signals contains all the information about the sound, about the incoming sound. But those are too weak to operate on them. So we need an amplifier to increase the power. So you'll find an amplifier next to the diaphragm that is increasing the power level of the received signal. Now this recorded signal up to that, this signal not yet recorded, this signal contains a lot more frequencies than the analog to digital converter can handle, right? So if ADC is running at 48 kilohertz, it literally cannot handle more than 24 kilohertz of signal. Otherwise, aliasing and other problems will happen. So what we need a filter that will throw away all the frequencies that my sampling, that my recording system cannot handle. So that's why we have a low pass filter that is removing all the frequencies above the 24 kilohertz. And this is the reason that the microphone is not being able to record in signal higher than 24 kilohertz. Okay? So we are, in the rest of the talk, we'll particularly focus on the system before this filter is being applied. Right? We know that once the filter is applied, all the frequencies that we are talking about, 40 kilohertz and higher frequencies, that will be gone forever. Then no matter how efficient ADC we use, those frequencies are not there. Those frequencies will not be recorded by the microphone. So let's look for the first two phases, the diaphragm and the amplifier, to see some opportunities if we can bypass this filter while the signal is passing through the system. Okay. Sorry, I think I was accidentally muted. So here, what we're trying to focus on is the first phase, which is called the microphone front end, the diaphragm and the amplifier. We'll focus on that to see opportunities to bypass the low pass filter to inject the signal, inject the high frequency signal to the microphone recorder or the ADC. Okay? So this front end is basically a linear system, which means if you give an input V in to that system, you'll get V out, and the relationship between this V in and V out is the linear equation, meaning V out is equal to A1 V in. It can be amplified, it can be attenuated with a factor of A1, but no nonlinear operations are going on. But let me tell you, this linear behavior is only for lower frequency signal. If we give the same microphone front end, higher frequency signal higher than 30 kilohertz, then we'll see that the same system will start behaving nonlinearly, which means the V out response cannot be represented well with only one A1 V in factor. It will require higher frequency factor, A2 V in square, A3 V in cube, and so on. Right? The nonlinear functions will require nonlinear function to represent the behavior. Now, this third and higher order terms is weak in general, so we can remove them. But the second order term is reasonably strong in regular microphones, and we can exploit it to shift our signal from the higher frequencies to the lower frequency range. Next, let me tell you how this fundamental nonlinearity in microphone can be exploited to make microphone hear what it is not designed to hear. Okay? Let me take a simple example. Let me explain everything with the help of a simple example. Imagine with a speaker, we are sending two frequencies, F1 and F2, and that is our signal V in to a microphone. When these two frequencies will reach to the microphone, say two frequencies are 40 and 50 kilohertz, that will appear in the frequency range of the microphone. Now, these two frequencies will pass through the nonlinearity, the V in square term. And if you do some simple high school math, you'll find that these two frequencies, sine F1 and sine F2, will lead to 4 different kinds of frequencies if it passes through this nonlinearity, this square term. What will happen? You'll find that frequencies 2F1, 2F2, F1 plus F2, and F1 minus F2 are appearing in your output. Now, first three terms are still higher frequencies, higher than F1 and F2. So all these frequencies, including F1 and F2, will be removed while the microphone filter is being applied on that. But look at this fourth term. This is the difference between two frequencies. And if F1 and F2 are chosen carefully, then this frequency can bypass the microphone filter, and has much lower frequency. It will survive the filter and it will end up being recorded by the ADC and by the microphone. It will get sampled and it will come at the output. As if this higher frequency F1 is being shifted to the low frequency F1 minus F2 with the help of the signal F2, right? The helper frequency F2. Now, F1 doesn't need to be a pure tone. It can be any signal. It can be any modulated signal that can carry data bits, that can be a jamming signal, or that can be a voice command that is trying to attack Alexa. Okay. So this is the high-level technique for this inaudible acoustics. If we take this particular implication, this attack scenario, now let's take a deeper look at, or more practical look at this, whether this kind of attack is really possible or not. When we realize this system, this low pass, this bypassing this low pass filter and delivering this inaudible high frequency signal to the voice assistant, we have found that the maximum range that we could achieve is 3 to 5 feet. Right? Now, that doesn't sound like a practical attack, because when it is attacking your Alexa, maybe the guy, maybe the thief is already inside your house. That doesn't sound like a bigger problem or a real attack. Maybe the real attack will happen when the person can trigger your Alexa from the parking lot far away from the outside of the house. We tried that. We tried to achieve longer range by pumping in more power to the speakers. But when we tried to do that, it didn't work. You know what happened? It started generating, the speaker itself started generating audible sound. You know why? Why this high power is making ultrasonic speakers audible? Now, if you take a look at the speaker, you'll find that at higher frequency, this can also become nonlinear. And it's natural because all the components that the microphone has also present in the speaker, just in the reverse order. So if the microphone is nonlinear that we are trying to exploit, the speaker is also nonlinear. Now, at this time, we need to avoid it to avoid generating audible sound. So here's the problem. When we are trying to send this signal through the speaker, say V in is passing through the speaker, which also has this nonlinearity, that is generating the actual signal, high frequency signal, because of the linear term. But when this V in is passing through the nonlinear term of the speaker, it is generating component. One is higher frequency and one at the lower frequency. Now, we do not care about the higher frequency signal because that is inaudible. That is inaudible too. So that will be inaudible to human ears. We do not care about the higher frequencies, but the low frequency component that is being generated because of the nonlinearity of the speaker, we need to take care of that, because that will fail the purpose of generating inaudible command, right? We are taking this attack as our applications or implications, and we are trying to see what is happening with that. And we have found that to realize this kind of attack, we need to take care of this low frequency component that is being generated at the speaker. Okay. So how can we do that? Maybe the first intuition that comes to our mind, why not modify the signal V in a way that it will cancel this low frequency component at the speaker. Right? Now, this is a valid argument, but we have found that this nonlinearity in the speakers are time varying, and it has some reverberations, and it has the power dependency. So it's really hard to estimate the nonlinearity of the speaker and design some coding technique that can cancel this low frequency leakage. So that motivated us to design something called leakage optimization that I'm going to explain next, how we can deal with this low frequency leakage at the speakers. Right? Please ask me questions if you have any at this moment. So next I'll talk about how we can do this leakage optimizations at the speaker. So imagine that we are sending this signal VF, high frequency signal VF through the speaker, and first component, the high frequency component, will be generated the high frequency at the microphone right at its place. We do not have any complaint about this. But when it is passing through the square term in time domain, in the frequency domain, it's the convolutions of the same thing, the VF with itself. So it will generate this low frequency component. Interestingly, the bandwidth of this component and the shape of this component is dependent on the bandwidth and the shape of the actual signal VF. So what if, instead of sending the entire band of signal, what if we chop the signal into a narrower band and pass it through a speaker? Then it will create that component, that part in the high frequency range. It will generate the low frequency component, low frequency leakage. But this time, the leakage is of the very narrow bandwidth because the actual signal that is passing through the speaker has a narrow bandwidth. Well, then we can take another part of the actual signal and pass it through a second speaker, a different speaker. Then we'll see that because of the linear component, it will generate this next part of the signal right at its own place in the higher frequency. This time, it will again generate the low frequency component, but this time it's again at the baseband, and it is superimposing on the top of the existing leakage. So if we break this signal into the multiple pieces and send it through the different speakers, then we'll see that all the components, because of the linear term, they are being generated at the right place at high frequency. But this time, all the low frequency components are on the top of each other. They are superimposed on the top of each other, and the bandwidth of that low frequency component is much narrower. Okay? That's nice. So this chopping compresses the leakage bandwidth. Interesting, right? But if you take a closer look, you'll see that the bandwidth is compressed, but the total energy is not reduced. It's just there, it's just on the top of each other. How can we deal with that? But at the same time, this chopping gives us two parameters to control, right? We can select the number of chops that will, and also we can select individual bandwidth of all those sections, all those divisions. Those two knobs gives us the power to control the shape of this leakage. And fortunately, or rather unfortunately, human doesn't hear all the frequencies the same level. Human hearing threshold looks something like that curve. So you can see that we have higher margin at the low frequency components and lower margin at the higher frequency end. So with these two knobs, if we can play with this well, we can keep this leakage, we can optimize this leakage to remain within the human hearing threshold. And that will be practically inaudible to human. You can tell that this is a max mean optimization problem with the number of sections, the bandwidth of individual sections. We solve this problem to find what can be the individual chops and how can we transmit this to separate speakers to practically keep this leakage under human hearing threshold. I have a question here. Let me take a look. Mukalika Maiti says, what is the theory behind the fact that at high frequency, the microphone and the speaker shows nonlinear behavior? How does this nonlinearity is predictable? That is, we know that what frequency components are there. Wow, that's a nice question actually. So, you know, according to my own experience, and as far as I know, that all these physical phenomena are nonlinear. They are truly nonlinear. You will find infinitely many terms if you try to record their responses. For our own purposes, because we are very good at developing linear systems and we can deal with this linear system very well, we try to design, first of all, we try to approximate that to linear system, and we try to solve it with linearity. But in reality, there are non-linearity in practically anywhere. Now, these microphones and the speakers, those are designed to operate at a particular frequency range, and it was made linear for that frequency range. While we are trying to send higher frequency component, then the features, then the system doesn't remain linear, doesn't remain with its natural operation range, and it started showing heightened amount of nonlinearity than it's supposed to. And that is the opportunity that we are exploiting here. Hope that answers at least partially that question. If you have some more questions, we can talk about that towards the end of this talk. All right, so let me summarize this technique at this moment. So like we said, this chopping, what we are doing before sending the signal, this can be anything like the communication signal, it can be the jamming signal, anything. We are first chopping it to multiple pieces and sending it through multiple speakers that all the individual pieces are getting together at the microphone, and that is recreating the high frequency band just like we have transmitted. Right? And because of this, with the optimizations, we are managing the low frequency leakage to keep it within the human hearing threshold to make it practically inaudible. Now, when it appears to the microphone, we are also at the same time, we are also playing this helping signal F2, such that both of these two signals will mix with each other. And this component, the higher frequency component, will get shifted to the lower frequency region before the microphone is recording them. And that's how microphone is receiving this signal as if it is receiving any natural sound. So let me show you one of the implementation that we have done for that particular technique. Here we can see the speaker array for leakage optimization, and this time we are sending the same command from a much farther range. Let me play that video. And it played the same command, and
the United States capital city is Washington, D.C.
Alexa responded in the same way. Right? So let me summarize this part. Before I do, let me tell you that not only Alexa, we tried this system, tried this inaudible command with many different devices that comes with a microphone, like hearing aids, camera, iPhone, Android phone, smartwatch, laptop. And we have seen that all the microphones that these devices have within them, they all show this nonlinearity and they all respond to this inaudible command. So we can use them as our victim to our attack or as a way to communicate data to these devices. To summarize this first part, the inaudible acoustics is a new primitive that makes inaudible ultrasound audible to microphones, regular microphones, that can make different applications and attacks possible, including communication, privacy preserving jamming, and attacks. Next, I'll move to the next topic, the communication through physical vibration. But if you have any questions regarding this particular topic, please ask me right now. Avijit is asking, so can it be used to whisper using hearing aid? Yes, unfortunately, yes. So we should be able to use it for noise cancellations and sending some secondary data to the hearing aid. But we have found that it can be really annoying if the attackers are exploiting this technique to send jamming signals to someone who is wearing hearing aid. This can be a severe security threat, accessibility privacy threat to the users. And later, I have not included this in our in this talk, but we have also developed techniques to identify this kind of signals, this non-linearly generated signals, and detect some attacks in voice command and voice commands in voice assistant, and also try to show some directions to prevent or filter out this kind of signals in new kinds of new types of microphone design. But to answer this question, yes, unfortunately, someone can generate some annoying inaudible sound to hearing aids. All right. If we do not have any more questions, let me move to our next topic, which is communicating through vibration. So I'm rushing a little bit because of the time. So let me start with this topic. Like I said, the smart devices like smart watches will come with this vibration motor that is generating this haptic feedback. If you break open this vibration motor, you will essentially find two main components. One is a magnetic map and the other one is a coil. Okay? If you give alternating current to this coil, it will create a varying electromagnetic field that will push the magnet or attract the magnet in a periodic fashion to make it move to and fro in different patterns to generate this vibration. This essentially gives us a handle to control the movement of the magnetic mass, and therefore it can help us to modulate the vibration that is being generated. So this is a great opportunity, because if we can control this AC signal that is coming to this coil, then we can precisely modulate the vibration. We can change the pattern of the vibration that is being generated. And with that, we should be able to generate some signal, some vibration signal that can pass through human body. And at the same time, there are mobile devices come with sensors, motion sensors like accelerometer, that can sense ambient vibration. So if we are sending some modulated signal using this vibration motor, that will pass through the bone conduction, if we can design it in that way, that will pass through human body to human bone, and this vibration will be able, the smartphone or any smart device with this motion sensor should be able to pick up this vibration when the person is touching that device. Okay. And we have shown that we can control the vibrations in a way that human cannot feel this vibration while it's passing through human body. And it will be completely transparent to human body when the vibration is passing through the body and through bone conduction. Although we are being able to send lots of data through that, you will not be able to perceive anything, any vibration. Okay, so like I said, if we can do that, we should be able to data communication through physical touch. And apart from this touch-based communication, given that this vibratory communication is not sending out the signal in the air, unlike any other RF communication, it has a notion of security, given that the signal is confined within the physical contact between the transmitter and the receiver. So it can give us some extra layer of security while we are targeting some specific applications like maybe the password exchange or maybe the credit card information exchange at the point of sale. Okay, so let me briefly skim over the ideas that we have developed around this vibratory communication. So we have the vibration motor and the vibration sensors, right? So no one can stop us from communicating through that. We should be able to turn on and off the motor in a specific way to encode 0 and 1 to send information to the accelerometer. The accelerometer will know that the vibration exists means 1, doesn't exist means 0, so we can send data. Unfortunately, this on-off keying-based communication cannot achieve higher data rate. We have shown that it will be limited by 10 bits per second of data rate. But the application that we are targeting, touch-based credit card exchange, that will require some higher data rate that may be higher than 25 kilobit per second. So in order to achieve that higher data rate, we need to deal with multiple challenges. That includes the vibration motor response is nonlinear. It has some resonance frequency somewhere. The medium is also affecting different frequencies differently. The accelerometer has a limited bandwidth. It cannot have more bandwidth because it's designed in that way. It cannot have two-way communications and so on. So fundamentally, we dealt with this data rate, the lack of data rate, by designing a WaveDM-based communications. WaveDM is pretty common in wireless communications, a communication modulation scheme. So here, the core idea is to break the entire channel into smaller frequency beam, into smaller subcarriers. Those individual subcarriers are carrying low data rate signals, but we have lots of them. We have 200 or more number of subcarriers that is carrying data at the same time through this channel. And ultimately, we could achieve more than 32 kbps of data rate using this OFDM communication system that we have developed on this vibratory communication system. So let me tell you another challenges that we had to deal to achieve this data rate. That one is the limited bandwidth at the receiver. So the accelerometer has sampling rate maybe at most 3200 Hertz. So that fundamentally limits the total, the maximum data rate that we can achieve. So we need bigger bandwidth at the receiver, right? This is very basic. We cannot overcome that. To have better sensor, to look for better vibration sensor, actually we end up using microphone. Now microphone is also, the internal working is pretty similar to accelerometer. It has a diaphragm that is responding to the air vibrations, but it also responds to the physical vibration. Given that it has a lots of bandwidth, we should be able to capture a lot of vibrations, a lot wide bandwidth of vibrations through this microphone. So that will solve one of our problem of achieving higher data rate of communication. But I'll go to the problem, but first let me tell you how this is going on. So you have the smartwatch that has the vibration motor that is modulating vibration. That vibration V is coming to the microphone when you are touching it. Okay, it's passing through the response of the bone, H bone, and it's actually you are receiving very tiny, very faint vibration with the microphone, although very high bandwidth, comparatively higher bandwidth. So now you should be able to recover your data using microphone itself, right? But the problem is microphone is the sound sensor. So whatever signal that you are going to send, that will be mixed with the ambient sound. And the ambient sound is much stronger compared to your weak vibrations because the microphone was designed to record ambient airborne signal. What can we do? So we exploited the idea that most of the smart devices comes with another microphone built into that. So that can be used to sense the ambient vibrations. We can use some adaptive filter to separate out this ambient vibration from this vibration and signal combination, vibration and sound signal combination to achieve, to separate out our communicated signal through vibration channel, right? But the problem is both of these microphones are embedded on the same physical PCB. So they have a vibratory channel between them, which means the vibration from the first microphone will leak into the second microphone, and that will make both the data in both of the microphone correlated. That will throw the adaptive filter away, and that will make this correlated signal will make the adaptive filter to perform very poorly. To deal with that, what we exploited is that although it has a channel between these two microphones, that channel is a static channel, and we can know this behavior of this channel beforehand so that we can identify which subcarriers of the waveguide signals are heavily affected by the ambient signal and which one are not. And then we can only pass those affected subcarriers to our modified adaptive filter to separate out to recover very tiny, faint vibration signal, and we can communicate with that. Sandeep, do I still have some time, maybe 5-6 minutes?
Yes, sure, you can take 5-6 minutes. Yeah.
Sure. So that was the physical layer idea. And on the top of that, we developed the MAC layer that can deal with the single-sided communications. And also on the top of that, we developed multiple applications. So in the interest of time, I'm not going into the details, but I will just show you a demo with a very short demo with this vibratory communications. I've got one question, but won't this depend on the environment or the ambient sound? It has this cancellation, has some dependency on the ambient sound, but we have tested within various different conditions, and that actually, if we can control our data rate accordingly, we still be able to communicate even with a very strong ambient sound. All right, so let me show you a quick demo where you can see the vibration motor. It's a very ugly demo, makeshift ring that we have developed, vibratory ring, that has this vibration motor connected to the signal generator that is trying to send the encoded version of this picture, this logo, to the computer that has a system with 2 microphones. Let me just play this video so that you can see it. It is touching one of the microphone, and the laptop could decode the signal and recover the logo. It had some noise, but without much post-processing or coding, we were able to decode the data. Somojit is asking a question. The vibration also causes a sound. Can it create a problem? Very nice question, very clever question. So let me paraphrase this question. So this question can be like this. If the vibration motor, while it is sending the signal, it is generating audible sound instead of only the vibration that is combined with this physical layer. If it is generating some audible sound, can someone record this sound, and that will fail the secure notion of this vibration communication? We actually looked into that, and we have proposed the solutions where the signal, while it being sending the vibratory signal, it can create some jamming signal at the audio level or audible level that will have minimum impact in the transmitted vibratory signal, but it should be able to jam the ambient, the side leaking sound that the vibration motor is generating. So that was about vibratory communication. The third topic, I will spend one slide in it, and that is acoustic side channel. I kind of anticipated that we will run out of time at this moment. So how did we do that? The core idea is to record this ambient airborne vibration with internal sensors, and this time we have used the internal vibration motor. We have shown that ambient airborne signal can create small vibration inside the magnetic mass of the vibration motor. If we can record the response of the coil, we can see that this motion is creating a reverse voltage into, that is called back EMF, into this coil. And if we can recover that voltage and pass it through our custom speech recovery algorithm that we call vibraphone, that signal will be, we should be able to hear traces of human voice from that recovered signal. So to show you the difference or show you the efficiency of this vibraphone recovered signal that is recovering the signal from vibration, we played a sound through another speaker and recorded the signal with our vibraphone algorithm through vibration motor, and simultaneously we recorded with the microphone. So I'll just play two sounds. First, the microphone recorded sound, and then the vibramotor recorded sound, so that you can hear it for yourself. This is precisely recorded sound with the microphone, but now let me play the sound that was recovered by our project. There are lots of noise, but still you can hear the sound, the fundamental sound, and it's much cleaner. And I would like to mention here, we did not apply any machine learning algorithm here. We have just used our signal processing technique to recover the signal. And we hope that if we apply some machine learning algorithm and speech recovery algorithm with that, we can even remove the noise that we can hear in this recording. I think I have another question. Let me take a quick look at this. Saurav is asking, if we apply some algorithm to write the noise, then how much complexity of the system will increase? So, Saurav, is this regarding the questions of this particular vibration motor acoustic snooping or the vibratory communication? So vibratory communications, if we apply some algorithm to write the noise, then how much complexity of the system will increase? So definitely that will add a little bit of complexity to the system, but we have seen that given the the capacity of the regular microprocessor, we should be able to simultaneously recover or play the vibratory signal and generate the jamming noise at the same time. So we should be able to develop a practical system with both the systems running at the same time. Navjot is asking, instead of using the second microphone to separate the ambient sound, can't independent component analysis be simply used? That is true. We have applied not only ICA, some other theoretical way to separate out sound from ambient noise, but we have seen that the actual signal, the vibratory signal, is so weak that without any physical means to separate those signals, it is really hard to have good enough separation, good enough noise cancellation to recover high data rate communication, to achieve high data rate communication. Of course, with a simpler technique, with theoretical noise separation technique, we can recover some vibrations, but the data rate has to sacrifice. So I think that these techniques can be complementary to the system that we have presented, where we have used another microphone to use adaptive filter to separate out the WaveDM communication signal. All right, so let me move on. I am almost at the end of this talk. So this talk covered 3 of the topics that I've worked on. And apart from that, I have also worked on network noise cancellations, localizations, hardware fingerprinting, robotic network, and protocol design, core network protocol design. Recently, I've worked on acoustic eavesdropping that was also covered in multiple media outlets. And also I have worked on a topic where we have used acoustic signal to develop a lightweight defense mechanism on the resource constrained robotic vehicles and drones. So if the idea is that if you are throwing something directly at the drone for sabotage or for disrupting its flight, it should be able to find that some dynamic obstacle is coming towards that, and it can dodge effectively. So please visit our website to take a look at those projects. Mainly my research is around the cyber physical systems, wireless, personal computing, and mobile health. You will find you'll find lots of variety in my research. Please visit my website and send me questions if you have any. Thank you so much.
Yeah, thank you, Nirupam. So I guess that there is one more question in the chat box from Navjot.
Let me take a look. I think the ICA questions I have answered. Is there any other question?
Okay, the ICA question. Then I guess it's fine.
If you have more questions, please send me emails and I'll be happy to answer them.
Great. Okay, so I guess that the talk was very interactive and we got a good number of questions throughout from the audience.
I think there's an unanswered question.
That how much of these designs are dependent on present microphone speakers and applicable to future acoustic systems? Would not manufacturers correct these flaws?
That's related to the first topic, inaudible acoustic, I guess. So,
right.
Hey, Ambuj, hi. Yeah, so actually, the problem is really practical. So you know that there is a whole line of lots of such microphones are on the market already. And those are actually keeping microphone linear for a wider range of frequencies increases the cost. And because these microphones are that most of the devices are using are of a certain price range, to achieving them, to changing the manufacturing line to remove this nonlinearity altogether is kind of challenging. The other solutions you may think of, I'm sure that must have come to your mind, that why not have some low pass filter before the amplifier. But the problem is that also attenuates the signal significantly before if we apply low pass filter before the amplification. So there, theoretically, yes, it is possible to develop some microphone that can thwart this kind of attack. Maybe future microphone will try to adapt to this thing, and maybe I'll be happy to see some microphones that is coming out. But I've spoken to multiple people, and the idea that is coming out is that to keep the cost within some certain range, it is hard to achieve linearity for a wider range of frequencies. So that's pretty much where the state of the art is.
Okay, so thank you, Nirupam, for.
I have a question. Can I
Mukulita,
ask?
please go ahead. Yeah,
Yeah.
sure.
Really great talk, Nirupamda. So this question is like not a technical question, but so what is the good course to like or to prepare the foundation knowledge to start this type of work? As in,
right. So, thank you so much for asking the
breaking
question.
apart the sensors or the microphone. So typically the courses in CS curriculum, I'm not well familiar with the EC, but at least in BSU, that CS curriculum or something in typical colleges, so it is not there. So what is the basis of foundation knowledge for this type of work?
Right, actually, very nice question. So let me take a couple of minutes to answer that. And I think my answer will resonate with many other people who are working in the systems field. Because in the system research, you will find that you will require a wide array of knowledge, starting from a little bit of hardware if you are working on a more hands-on practical work, or you are trying to develop some practical systems out of your research. You'll find that you need a wide array of knowledge. You may need a little bit of knowledge about how this front-end signals behavior, how to deal with this frequency time domain representation of the signal. You will also find like how to deal with, how to do a little bit of signal processing. Then you will go to the next level. You will try to, if you're working on communications, you need to have some knowledge about the coding, the communications ideas, the bandwidth, how this related to different modulation schemes. At the same time, you will see that you will need some theoretical knowledge for higher level data processing and also networking. But I'm telling you that, of course, we need a wide range of knowledge to be able to successfully deliver a systems, IoT systems research. But it is not that intimidating, because if you start with some fundamental building blocks, fundamental knowledge that I will say touch upon a little bit of the signal representation part, little bit of a good foundations in linear algebra, in good understanding about how this some of the higher level data processing, maybe the learning and optimization algorithms are working. If you have some foundational knowledge in these parts, you find that gathering knowledge as and when we are moving through our PhD or through our research, you will find it easier to learn newer things based on those building blocks. So in my course, I have developed a course that's called Wireless and Mobile Systems for the IoT in UMD. And there actually I have tried to touch upon all these topics that someone will need to start working on the systems IoT kind of research, security, systems IoT, and this data related, embedded data related technologies. So that can be a nice point. If you get some time, please visit that website, that course website, and we'll find that what are the topics that I've basically touched upon. But the core idea is to have some of the fundamental knowledge, some fundamental subject into your repertoire so that you can build on that to understand a wide array of knowledge that you need for system research. Sorry for the long answer, but I think many of us will resonate to this idea.
Okay, thanks a lot.
Thank you.
Any other question? Okay, so if not, then let us conclude the talk by giving a big thanks to Nirupam for keeping our request in giving a webinar in SCM iMobile. So this is a very informative talk and a very interactive one. I guess that all the participants have enjoyed the talk, and I hope Nirupam, that we'll get your support in the future days of iMobile
Sure.
to build up a system infrastructure and a culture of system research from India, keeping in mind that our target about what Amit mentioned in the initial days, that we have very less number of or near to zero number of papers in the top system conferences from India. And one of the big objective of iMobile is to push people towards that direction so that we can come up with collaborations, ideas, and can do nice system works in the Indian academia while collaborating with the industries. And with that aspect, actually, this iMobile chapter that was also built up, keeping in people from both academia as well as industry. So that is our long-term goal. So we hope to get your support in the upcoming days.
Sure. Actually, I'm wholeheartedly thanking the organizing committee and Sandeep, you, for inviting me. It was a delight to be here and get a chance to talk to you all. Thank you so much for inviting me. And yes, to answer your questions, I'm wholeheartedly ready to help you in you and all the researchers from that community, iMobile community, in whichever possible way in my power to make it a successful chapter. It's a successful initiative. So please do not hesitate to reach out to me. And I will also definitely reach out to you guys for any kind of collaboration opportunities.
Thank you, Nirupam. And finally, thanks to all the participants for giving your time in the talk. So that concludes this session. Thank you, everyone. Take care. Bye-bye.
Bye-bye.